Hi everyone, I'm going to do a tutorial on hybridization because I understand that some of you are still having trouble understanding this concept. So to talk about hybridization, first we're going to start with a simple molecule, methane. And we're first going to go through and draw a Lewis structure and determine what we expect the geometry to be based on VSEPR. And then we're going to tie that into the molecular orbitals. Okay, so methane, CH4, carbon has 4 valence electrons, and hydrogen has 1 valence electron, and there's 4 of them in this formula. So our valence electron count total is 8 valence electrons. So we know we want to put carbon as the central atom because hydrogen can only form 1 bond. So we put carbon in the middle, and then we can start by attaching sigma bonds to each of the outer atoms. And at this point, we just want to check in on our total valence electron count and then see if we've accounted for all the electrons. And here we have. We have 2 electrons in each of these sigma bonds, so that's a total of 8 electrons. Now that we have our Lewis structure, we can think about what the molecular geometry would be. So remember, VSEPR tells us that we want to space electrons apart as far as possible. And this makes sense because electrons are negatively charged, right? So they're going to repel each other. So they're just going to naturally space apart around the central atom in a way that they're optimally far away from one another. Right? So I have electrons in this carbon-hydrogen bond, and I have electrons in this carbon-hydrogen bond, in this one here, and in this one here. So in this case, I have 4 sets of electrons that are going to repel each other. And so they're going to optimally space apart from one another as best as they can. So it turns out with 4 things around a central atom, the best way to get that arrangement is with a tetrahedral structure. So I have this one on the bottom left coming out of the plane, and then I have this other one which is going back into the plane. So I have this sort of this pyramidal structure on the bottom, and then this other hydrogen sticking up at the top. So all of the bond angles here are 109.5 approximately. So all 4 of these are the same. So this is the optimal way to space those electron pairs apart if we have 4 pairs of electrons. So that's why this is tetrahedral. Now let's go look at the atomic orbitals for carbon and hydrogen. The reason I want to look at the atomic orbitals is we use those and combine those to form molecular orbitals. Right? So if we take carbon atoms and hydrogen atoms and combine them to form a methane molecule, then we want to go from atomic orbitals to molecular orbitals. So let's look at the atomic orbitals for carbon. Carbon has an electron configuration, a valence electron configuration of 2s2, 2p2. And then hydrogen has a valence electron configuration of 1s1. So let's take a look at the carbon atomic orbitals in a little more detail. So remember, the s orbitals are a little bit lower in energy than the p orbitals. And then we have 3 degenerate p orbitals. I say degenerate, that just means they're at the same energy level because they're all 3 equivalent p orbitals, so they shouldn't be any different in energy. So we have 1 s orbital that's a bit lower in energy and 3 p orbitals that are in the same energy level. Now we have 2 electrons in the s orbital, and we don't have to just take that from here. We can also rationalize why we would put 2 electrons in the s orbital first. It's lower in energy than the p orbitals. So things tend to want to be in a lower energy state. And so we're going to fill up the s orbitals first, and we don't want to fill up the p until we're completely filled in the s orbitals. So now we have 2 valence electrons left. They go in the p orbitals, and remember, we want to not pair electrons until we run out of space. So here we can leave these 2 electrons unpaired. And now let's take a look at the hydrogen 1s atomic orbital. We're going to have an s orbital, and it's just going to have a single electron in it. Okay, so when we take atoms and combine them to form molecules, then we take atomic orbitals and combine them to form molecular orbitals. So in order to form a bond between 2 different elements, what you need is a free valence electron, or what I should say is an unpaired valence electron from each atom. So if you have 2 atoms that each have an unpaired electron, then they can combine to pair those electrons together and then form a covalent bond. So hydrogen is absolutely ready to form a new bond. It's got 1 electron in this s orbital, but it's also got a spot for 1 more. So it could attach to one of the free or unpaired electrons in carbon to form a new covalent bond. But we see there's an issue with carbon here. In the structure for methane, we drew out 4 bonds to carbon. But if we look at the molecular orbitals, there's only 2 unpaired electrons on carbon that could be used to form bonds. And we know carbon wants to form 4 bonds so that it can achieve the octet. So this is one reason for this so-called hybridization of orbitals. So if we imagine for a second what we'd like to do, the reason, remember, we have 2 electrons in the s orbital, and that's full, and then just 2 unpaired electrons in the p orbital, is because the s orbital is lower in energy. So if I was somehow to take these 4 orbitals, the s and the 3 p's, and combine them in a way or create an energy level such that they're all on the same energy. So if I had 4 equivalent orbitals that were of the same energy, and I took that orbital system and added 4 valence electrons, because I have 4 valence electrons for carbon, then what I would get is something like this. Now I have 4 free or unpaired electrons on carbon, each of which can be used to form a bond. And so now we can see how we could form 4 bonds to carbon if we somehow had 4 equivalent orbitals that were of the same energy level. Okay, so how do we do that? And the explanation for this is a little bit weird. The concept of hybridizing orbitals is a little bit strange, but we can kind of see where this is going. We have these s orbitals and p orbitals right now that are not of the same energy level, and we want to somehow mix them together and make them an equivalent energy level. So what we do is we hybridize them. And I know that seems a little bit strange, but if we have 1 s orbital and 3 p orbitals and we hybridize them together, what we're going to get is 4 equivalent sp3 orbitals. So let me try and explain that in another way. Let's use a convenient letter that actually matches here. So imagine instead what you have is 1 salt shaker and 3 pepper shakers. So I'm just going to give these s's and p's just like the orbital names. So we have 1 salt shaker full of salt, 3 pepper shakers full of pepper. These are different, right? One's salt, one's pepper. But what we could do is imagine we emptied out all these salt and pepper shakers into a big bowl that now contains both salt and pepper. And what's the ratio of those going to be? Because you had 3 full pepper shakers, you're going to have a 3-to-1 ratio of pepper to salt. So now you have this mixture of salt and pepper in a 3-to-1 ratio, or 1-to-3. So now what we're going to do is take this mixture of salt and pepper and put it back into the shakers. So now you're going to have a mixture of salt and pepper in each one of these. So this one is going to be salt and pepper, and the ratio is going to be the same as what we had for this combination here, right? We mix them all together, we have a 1-to-3 ratio, so now we have 4 equivalent salt and pepper shakers, which each have a 1-to-3 ratio of salt to pepper. So this is really equivalent to what the hybrid orbitals are doing. So let's go ahead and write that ratio though. So for each of these salt and pepper shakers, what we have is 1 part salt for every 3 parts pepper. So this is really the same as what we're looking at for an sp3 hybridized orbital. We just leave out that 1 because it's understood to be 1 if it doesn't have a number. So that's sort of the concept here that we're using to hybridize these orbitals. We take 2 things which are initially different, salt and pepper, we mix them all together and then redistribute them so that we then get 4 equivalent things back out. So if we do that with orbitals, then what we get is 4 equivalent sp3 hybridized orbitals. And because now all the sp3 hybridized orbitals are on the same energy level, then we expect to fill these one at a time, so we end up with 4 unpaired electrons, and now this thing is capable of forming 4 covalent bonds. So if I draw out the orbitals for hydrogen again, hydrogen, remember, has a 1s orbital. So the first hydrogen that we're going to add here has 1 electron in an s orbital. And then the next one has yet another one in the s orbital. So remember, in our molecular formula up here, we're dealing with CH4, 1 carbon and 4 hydrogens. So we can draw out the 4 hydrogens. So down here are the orbitals for carbon, and down here are the orbitals for 4 hydrogen atoms. So now we're going to take these orbitals and combine them to form covalent bonds. And what we can see here now is each one of these orbitals that we've drawn out has one unpaired electron. So it's got one electron that's capable of forming a covalent bond. So these two are going to combine to fill an orbital, these two, and these two. So now that's where we're going to get our 4 carbon-hydrogen bonds from. So now let's talk about this concept in terms of pi bonding. So now I think we can see how we're getting the sp3 hybridized orbitals. So what happens when we have something that has a pi bond? So this will explain sp2 and sp3 orbitals. So when we have pi bonds, let's come up with an actual structure that we can look at by way of example. So I'm going to take this compound here. We have a double bond between the 2 carbon atoms. We know from the steric number of this, so let's kind of look at 1 carbon atom specifically. So we have to do this for 1 atom at a time when we're thinking about hybridization. So let's look at this carbon atom right here. So what is the steric number of this carbon atom? The steric number is 3. The steric number is simply how many different things are around it. So is it a lone pair or an atom? So you're basically looking for how many atoms and how many lone pairs are around it. So the number of atoms around the highlighted carbon is 1, 2, and 3. It doesn't matter that there's a double bond to this carbon. What matters is that there's 1 carbon atom bonded to it. So we have a total of 3 things around here, which means we have 3 sets of electrons that we're trying to space apart. And so the steric number being 3 tells us that the hybridization is going to be sp2. So why is the hybridization sp2 for pi bonds? Well, let's think about what happens with a sigma bond. So we know the hybrid orbitals here are sp2. So the sigma bond is going to be formed of 2 sp2 hybridized orbitals. So sp2 looks a little something like this. A little bit different from a p orbital because you're overlapping an s orbital on one of those p orbital lobes, so it's just kind of making it a little more spherical in shape. So the way the orbitals combine to form a sigma bond is that the orbitals overlap head to head, which means I'm going to turn these 2 orbitals on their sides. So I turn these 2 orbitals like this. We're going to overlap those larger lobes. And so remember, there's a carbon atom in the middle here, so let me go ahead and draw that. Carbon, 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 and carbon. So now what you see is that all the electron density ends up squarely between those 2 carbon atoms. And that's why sigma bonds overlap head to head, because it's going to give you the optimal overlap of electrons in such a way that most of the electron density is going to be between the 2 atoms in which you're trying to form a bond. So the most stable way you can form a bond between 2 atoms is to have the electrons right in between the 2 atoms. Okay, so once you form a sigma bond, then you can form pi bonds. So pi bonds are formed of pure p orbitals. And the p orbitals are going to overlap side by side rather than head to head. And the reason they overlap side by side is because if you overlap them head to head, you're going to have electron density in the exact same region as the electrons that are in that sigma bond. And you can't do that because electrons are going to repel one another. So you can't have them overlapping with where the sigma electrons are. So instead, if we overlap them side by side like this, now what we get is something that looks like this. So let me go down here. So when we overlap them side by side, what we're going to get is something like this. And now you can see we formed sort of this sandwich structure that we could overlap without interfering with the sigma electrons. So let me superimpose those overlapping p orbitals with the sigma bond that I've drawn here. So I would include those pi electrons right here. And so now you can see that they don't interfere with the sigma bonding electrons. And so the p orbitals are going to be the most effective way to overlap if you can't do head-to-head. So since the sigma bond is already doing the head-to-head overlap, the pi bonding needs to be the side-by-side overlap. And the most effective way to get overlap if you're doing it side by side is to use a pure p orbital. Because if I use something that looked like the sp3, so something like this, then you can see that the bottom isn't going to have as much overlap as the top is. So here we want to use pure p orbitals for forming the pi bond because that's going to give you the most effective overlap between those two orbitals. Let me go ahead and get rid of these. So what that means is every time you form a pi bond, you need to take one p orbital out of the orbitals to which you can hybridize. So let me clarify that a little bit. This carbon here needs to form a pi bond to its adjacent carbon. So it needs to reserve one p orbital to form that pi bond. And so in order to do that, initially it has an s and 3 p orbitals. If I need to reserve one for pi bond, then what do I have left to hybridize? I've got an s orbital and 2 p orbitals. And so with something that has a pi bond, when it does hybridize its orbitals, it's going to hybridize it with one less p orbital. So if we have one pi bond, instead of being sp3 hybridized, we're then going to get sp2. And then likewise, if we have something like a triple bond, so let me go ahead and draw this here. If we have a triple bond to carbon, now I have a sigma bond and 2 pi bonds. So here I'm going to need to reserve 2 p orbitals on each carbon to be able to form those 2 pi bonds. So the hybridization of this carbon atom, if it initially has an s orbital and 3 p orbitals, and we have to reserve 2 for pi bonds, then what we're left with is sp. And so the hybridization of this carbon atom is going to be sp.